This conference will now be recorded.
Hello everybody, Jordan Girth here from the National Weather Service Office of Observations. I hope you're doing well on this Thursday. It's a beautiful day for many in the central and eastern United States. This is a Satellite Book Club seminar series, session number 25. Today we're joined by Dr. Huan Meng, physical scientist at NESDIS STAR, and the title of her talk is Radar Satellite Blended Snowfall Rate Product. Just a few reminders before we get started in the formal introduction that this session is being recorded, so if your colleagues are unable to join us today due to shift work or other reasons, you can point them to the VLab and they can catch it at their next opportunity. There will be an opportunity for Q&A after the presentation. Go ahead and put your question in the chat if you would, and then we'll field them through there. This week, the discussion after the presentation will be facilitated by Nick Langley, the Science and Operations Officer at the Weather Forecast Office in Marquette, Michigan. If you're interested in being a future presenter, please feel free to reach out to us. We'd love to have you, especially if you have an application that is relevant to our field staff. The training team can help create training materials that may be unavailable related to satellite, or you might just need help finding them. Contact Brian Mata at the Office of the Chief Learning Officer for information or questions regarding that. I'd just like to thank the Tower S team, particularly Lee Byerly and David Blutis, for supporting this satellite book club, the Office of the Chief Learning Officer, and the GOES-R and JPSS programs. Without further ado, I'd like to introduce Dr. Huan Meng, is a physical scientist at NESDIS STAR with a research area in passive microwave remote sensing. She's been working with a team of scientists from the Cooperative Institute for Satellite Earth System Studies at the University of Maryland to develop satellite-based and radar-based blended snowfall rate products. Winter's just around the corner. Huan, welcome to the Satellite Book Club.
Thank you, Jordan, and thanks to the Tower as a team for giving me this opportunity. I'd like to talk about the radar satellite blended snowfall rate product that we developed at NESDIS and University of Maryland, CISESS. And these are our developers and collaborators, and this acknowledgement for their contribution. Okay, so mSFR, first of all, it's a liquid equivalent snowfall rate product, so it's a QPE. The radar part comes from MRMS, instantaneous precipitation product, and that was developed by the NSSL. And the satellite product is the NESDIS operational snowfall rate product. The MRMS instantaneous QPE includes rain, snow, and some other forms of precipitation. And they use reflectivity from a network of radars in CONUS and Canada. And it has high resolutions, space and time, 1 kilometer by 2 minutes. And the issue with the MRMS product is it has limited coverage in mountainous and remote regions. That happens quite often. And also when there's a snowstorm, the quality degrades. The images on the left, those are the MRMS. Actually, this is hourly precipitation to show better precipitation pattern. And there's also this MRMS precip flag. So from the flag, you can see some are rain, some are snow, and that's the flag we use to extract the snow information. The image on the right shows the radar quality index. So in the west, you can see there's quite a bit of radar gap, and in the east, usually it has pretty good coverage, except that when it snows, the quality degrades, so you can see the gaps. So the SFR, which is our satellite product, it is also a QPE, and we use passive microwave measurements to retrieve SFR. And right now we have 10 polar orbiting satellites we can use for this product. So unlike visible and the IR measurements, the passive microwave signal can actually penetrate clouds. So it can get information about the precipitation itself, so it's more suitable for precipitation retrieval. the resolution of SFR is sensor dependent. The best is a GMI, which is a NASA sensor. It's 4 kilometer by 7 kilometer. And for the ATMS and MHS sensors, those are the NOAA and EUMETSAT satellites. Those have variable footprint size. At nadir is 16 kilometers. The issue with the SFR is it doesn't have as frequent measurements as, like, say, radar. These are polar orbiting satellites. So with 10 satellites, we get about 20 SFR estimates. That's 20 satellite overpasses per day. This is at the location in mid-latitude, but we do get more in high latitude. So thanks to SPORT, SFR is already in AWIPS. And there's also a drop-down list. I've learned that you can choose the snow to liquid ratio, so you can convert the liquid to solid, which is what the weather forecaster needs. So the image on the left is AWIPS-like SFR image. On the right is equator crossing times of the satellites we use, plus some more. So if you look at the red arrows, those indicate the satellite we use. And this is a 12-hour time in a day, so you can have an idea how the satellite distributes in time. So we developed the mSFR in response to forecasters' need for looping capability. Apparently, that's very important for weather forecasting. So the blended product takes advantage of the satellite's broad coverage and radar's frequent measurement. So that gives you these images give you an example how SFR can fill in the radar gap. On the left is mSFR, in the middle is MRMS, and on the right is a modeled Snowfall, hourly Snowfall product that's from NORSC. So you can see how in this magenta colored circle, in that area, MRMS missed the precipitation because it falls into the radar gap, but the satellite fills in that gap. So the NORSC give you an idea how, in general, that area does have some snow. So in order to generate the mSFR product, we use direct broadcast data to generate SFR. Right now we have 7 satellites that we can use to generate mSFR, because there are 3 of them, and they don't have a direct broadcast capability, and so we can use them. And the direct broadcast data comes from the University of Wisconsin. We use a rather simple blending technique right now. We start with MRMS grade, and we'll quality control MRMS, which means we'll set a flag if MRMS is of low quality. They have a radar quality index. If it's less than 0.3, then we don't use it. Or if MRMS doesn't have observation, that's radar gap. Or if there's no snow, that includes any forms of precipitation except snow. Then we set the flag, and then we assign the QC MRMS to the grid, and then we add the SFR estimates where MRMS is flagged. So, this is an important feature to mention. The SFR and MRMS are actually not synchronous. SFR lags, well, MRMS is 30 minutes ahead of SFR. How do I say that? SFR is matched to the MRMS 30 minutes later. This is because satellite is most sensitive to snow in the atmosphere, and it takes some time for that snow to fall to the ground. Our study indicates that the highest correlation between SFR and the MRMS is 30 minutes. So if you, it's with a 30 minutes time shift. So if you look at that plot, that shows the correlation between SFR and the radar. both the correlation and root mean square have the optimal, about the optimal, the result at 30 minutes. So that's the reason behind that time shift. As I mentioned earlier, actually, the mSFR temporal resolution is 10 minutes. So that gives you the looping capability, and the latency is 6 minutes on average. And this is a CONUS only product. So this is an image of like AWIPS-like image. This is what I get from the sport website. In AWIPS, it should look quite similar to this. So you can identify where's satellite, where's radar by the footprints, by the resolution. SFR always has coarser resolution than MRMS. Okay, so SFR and mSFR can be used for weather forecasting. Right now, we at University of Maryland in the Cooperative Institute to generate the SFR and the mSFR product at real time. And the data, Sport comes get the data and then converts them to AWIPS ready format and distribute to some WFOs and near real time. Using DLM. There are some websites where you can see this product in near real time. Sport has mSFR page, and SFR is also shown on the web, both at Sport and at CISESS, University of Maryland. And I just want to mention that if there is interest to see a particular area, we can generate a page for you at CISESS. Okay, so this is a use case in northern High Plains from last year, and this was a case reported by Tom Clemens from Glasgow, Montana. So they have access to mSFR through Sport. And so they use it, and I'll just read what he said here. What was amazing with this case, well, maybe I should show the, okay, so, oops, sorry. This is supposed to be an animation. I don't know why it's not showing. But in any case, so what Tom said was, what was amazing with this case from October 9th, we were also looking at the advective layered precipitated water, and we could see the dry layers surface to 850 millibar and 850 millibar to 700 millibar, approaching the boundary from the north-northwest, where the mesoscale band of heavy snow was occurring. And then within the next hour or two after the drier air arrived, the snowfall rates rapidly diminished. Both of these products used together provided an advantage for SA and for providing weather and social media updates on the heavy snow band. So on the top, those two images are the advected layered precipitated water, and this is a product developed by University of Colorado State University, and this is mSFR. And this is also from the same event in a later time period. Okay, so what I want to mention here is, unfortunately for this event, at the time we had a problem with data processing, so only 2 satellites were included. But now we have all 7 satellites in there, so you will get more satellites overpass. So this is just the image I just showed earlier, and it's zoomed in. So we were curious about how well the satellite was reporting the precipitation, because it has, you know, quite a bit more coverage than radar in this case. And so these are these boxes are the surface report. And as you can see, the majority of them do have snow. So that's kind of reassuring to say that satellite is doing a decent job. And this is actually a good one to see the difference between radar and satellite in terms of the footprint size. And you can see this bigger bigger footprints, and these are all satellite. Okay, so this is another case. Because satellite sees higher than radar usually, so you can use it for short-term forecasting under the right conditions. This is a case put together by Sheldon Castleson. Okay, so this first, so he reported that SFR, well, okay, come back a little bit. Just want to stress that SFR, this is about SFR, not mSFR. So at first, this was a case in Birmingham, Alabama. So at first, at 10:47 Zulu time on January 28th of 2014, there was no snow observed at the surface, but SFR, which is the middle image, was showing some snow, but that was in-cloud snow at the time. And then, by 15:53, everybody was reporting snow, and of course the snow gets more intense in Snowfall, in the SFR product. So then if you're interested, you can go into this. This is a post put together, as I mentioned, by Sheldon, and it's posted on a NASA Sport web post form. Okay, so we're doing a lot of work right now for the SFR, and so just have some list some of these activities. Some are planned for the future, some are ongoing. One thing for the mSFR we do want to do is to improve the blending technique. We would like to explore data fusion. So right now the blending technique is rather simple, but this both SFR and MRMS are, we have continuous development going on, and by no means MRMS, especially MRMS Snow, is perfect. So we would like to take a harder look at that product and see if, under what circumstance we can put in satellite instead of using radar data, even though it has, the quality index is above, it's a 0.3 or higher. So, and then also we would like to do a better spatial temporal matching between the two products. Right now it's 30 minutes, and that's based on our statistics, but it's not ideal in every circumstance. So, and also MRMS has Alaska product that's experimental, and they're evaluating it. If that proves to be a good product for snow, then we would like to do mSFR for Alaska. That would be helpful, we believe, for Alaska, since they don't have very good radar coverage there in general. And also, we have several projects going on to develop SFR. One thing we're doing, and it's showing very good preliminary result, is we want to extend snowfall detection to even colder region, and this can be very helpful in mountainous regions where it can be colder than what we can apply SFR right now. and we're using this with AI, and that's a powerful tool. We're also improving the algorithm, the SFR algorithm itself. Such as using more advanced macrophysics. And also we have a project to extend the SFR over ocean. So many exciting development is going on. And this, if SFR is improved, the mSFR will benefit. And also we have some, we're waiting for some new satellites to be launched, one next year and 3 more the year after. And also another development we're doing on the side is to put SFR and mSFR on Google Maps. So then if people are interested in a particular area, they can go in there, zoom in. So what you can do with Google Maps, you can do it with a product laid on top of it. So that would be great. I think that's all. Okay, so here's just the summary. We have Overland SFR product right now, and it's produced from 10 satellites and provides 20 SFR estimates per day. And we blended with the NSSL MRMS product to create a spatiotemporally enhanced mSFR product. Both of these products can be used in weather forecasting. They provide situational awareness during snowstorm. They can have the looping capability and makes it easier to do storm tracking. And also SFR under the right conditions can be used for short-term forecasting. And we continually develop this product and that we both improve the product and also allow us to bring in more satellites into the product suite. And I believe that's all. Okay, I'm ready for questions.
Thank you very much for your presentation, Dr. Huan Meng.
Sure.
So we do have some questions coming in. While those are coming, I'll start out with one here. Just what is your plan for transitioning the mSFR product into operations?
Okay, so right now, as I mentioned, we generate the product at the University of Maryland and send it to Sport, and Sport sends the data out to some participating WFOs. If we transition to operation, we will be able to enjoy the stable data distribution with hopefully 24/7 support. Traditionally we transition product to ASPO, that's the NOAA NESDIS operation. So to go through that process, we need to bring the direct broadcast into operation. So that can be a challenge. The second part is probably not that. Well, there are different channels to distribute the data to users. And I've learned that for the distribution part, the Tower S has the capability to, they can connect to many users at NWS. So that will be the preferred path for bringing this product into operation. The data production part at STAR, that's the agency I work for. We have this moderate assurance processing. I learned that it's going to the cloud. So hopefully we can get the product into the cloud processing. Then that will be the support we can, that would be the way to support the operational product of the mSFR. Yeah, so either go to ASPO or go through the moderate assurance at STAR will be the way to get the product into operation, but the distribution will be through Tower S. That's what I think.
Great, thank you. And just in the meantime, until we see it in operations, is there anywhere that we can grab archived data if we wanted to go and look at past events?
We do have the archive data. That's actually not online. We have real-time data. If anybody is interested, we can talk to us. We can point you to where to download data. For the historical data, we can definitely stage the data for you, and you can look. I want to mention the data is in HTF EOS, which is kind of old format. So if there's particular interest for an event, down the road, we can develop the product into different formats that can be used easier. So yeah, so contact us.
Great, thank you. And we've got a bunch of questions that came in here. So the first one is from Michael Stringer, and he's asking, are there any plans to use the GOES-R data?
Right now, we don't have plan to use GOES-R data. The issue with that data is for product retrieval, it is a little difficult to use because it's IR based. It's IR, and we actually had a small project to use GOES-R data to propagate our product, which is very good. That's a good way to use the product, to use the IR measurement. We do want to look into IR to help us to find like cloud height, cloud top height, things like that. That will be helpful. But right now we don't have any project to use IR. Actually, I should mention we did submit a proposal and recently, and part of the proposal is to use IR to look at the cloud top height and other possibilities.
Thank you. And we're just gonna pause right here, and I believe David's gonna take over for a minute.
This is Jordan. I'll just do a bit of a formal wrap up for those of you that have to depart at the bottom of the hour. But if you're interested, we're going to continue some of the discussions. If you have a little more time, Nick and Huang, we'll continue talking about this because I do see there's some important questions coming in. So for those of you that have to go, please consider filling out our survey that David's posting in the chat now. We'd love to hear your feedback on the Satellite Book Club. If there's any topics that that you're interested in, please feel free to let us know about that. Next week, I hope you're going to join us on Thursday, November 12th at 12 noon Eastern Time. Steve Cobb, Science Operations Officer at the Weather Forecast Office in Tulsa, is going to demonstrate the application of GLM products during a QLCS quasi-linear convective system across Oklahoma back in May 2019. So look for an email from the Tower S team on that. Otherwise, thank you for your time today. For those of you that have to go, if not, hope you continue to stay online for the discussion. And with that, we'll turn it back to you, Nick.
Thank you, Jordan. All right, so yeah, we'll keep going with questions, and yeah, thanks for everyone to continue to stay on for this discussion. You noted the too cold for retrieval. And this is a question from Scott Lindstrom, and he's just wondering, how cold is too cold for retrieval?
It is the hard limit is on satellite measurement, but that has a high correlation with the surface temperature. So the 2-meter temperature is about 7 degrees Fahrenheit. So below that, we don't do retrieval at all. Above that, close to that range, the performance really is for snowfall detection performance degrade. But we're pretty comfortable with a higher temperature.
Okay, just a little side note question off of that question. Is there any issue with over water, such as over the Great Lakes?
Right now, we don't have retrieval over water. I mentioned that we have a project to develop SFR over water. So that is an effort going on, and in 1 year that project will wrap up. So hopefully we can get something into that. We can have over water coverage, and soon after that.
Okay, thank you. Yeah. Our next question comes from Michael Jamilkowski, and asking on the slide showing the mSFR example over the CONUS, is the variation in pixel box size due to the different satellite sensor resolutions or the distance from nadir to the edge of the scan, or both?
That actually shows the native resolution of the satellite pixel. So that pixel size will vary by sensor and by how far away they are from the nadir. So we put everything on the MRMS grid, and if the satellite footprint, is, for sure it's larger, so you will fit many of the MRMS grid points in there, and however large the satellite footprint is, will fill all those MRMS grid points with the satellite value. So that's what it is.
Okay. And then we got another question from James Ledoux, and he's asking, he could see a challenge with subcloud sublimation affecting the estimates at the ground far from individual radars. What's your impression about the satellite product's sensitivity to the same sublimation?
Right now, we're not considering that effect. So what a satellite sees is, the cloud, the in-cloud precipitation, like because in the algorithm, we actually make the product represent the snow at the cloud base, basically. So, what happens below that, we're not really considering right now, and that is an important fact that we want to consider in the future. But to do that, we'll have to use model data to help us with and need to learn that process. So.
Okay, and thinking back to some of those images too, I think it was on slide 4, you showed it looked like down around Salt Lake, like maybe it was picking up on some snow where the radar wasn't, and just got me thinking, does it matter if it's a shallow precipitation process, like really shallow upslope flow or lake effect snow? If obviously once it's on land, that you can that affects the quality of the product or its ability to detect the snow?
That would be a problem. Yes, satellite does have issue with seeing very low, very shallow precipitation. So we don't perform well at all for shallow snowfall. Yeah.
Okay. And I'll make sure I'm not missing any here. So here's another question from Mike Jamilkowski again. Sorry if I did not pronounce your last name correctly, Mike. What are the chances that geo-satellite data will be more useful to you in the geo-exo era?
If there is a geo microwave sensor on the geo platform, that'll be our dream come true. That's what we would really like to have. Yeah, because the way we see it, the infrequent measurement from the orbital satellite is a major drawback of the current polar orbiting satellite-based products. So, and for precipitation, which is a very dynamic process, if we get frequent measurements, that will be just perfect. Yeah.
This is Jordan. Could I just ask a follow-up question on that? And
Sure.
I know Mike's last name is a little hard to pronounce. We just call him Jammer in the field. So good question, Jammer. But one of the aspects of the geostationary is you have the ability to get consecutive images over a relatively short period of time. Would that capability help you in situations where you have a situation where snow is on the ground or other challenges that you have previously with quantifying the snowfall rates, Huan?
Yes, because if I understand your question correctly, so if we have a continuous measurement, then just that change in the measurement, we'll be able to quantify a few things. One thing is we can take into consideration of the emissivity change on the ground, how to see how when you're from no snow to with snow cover, that change will be very helpful for us to improve our algorithm. And also we'll be able to see, this is another aspect of it, we'll be able to see how the precipitation develop and diminish. So we can see what stage the system is at. So when satellite has, what satellite sees is a snapshot. So if you only have that one snapshot, and the measurement, satellite measurement can look quite similar before, like at different stage of the storm development, but the read can be quite different. So if we know that temporal evolution of the system, that will be that adds to a lot of information content for us to derive a better product.
Thanks, good feedback.
All right, so now we have a question from Mike Stavish, and he says, I think seeing the data, snowfall rate in inches per hour would be most useful for forecasters. And I see that there's some canned liquid to snow ratios applied for AWIPS. Where can we find the AWIPS setup?
This is because right now SFR and mSFR is distributed by sport, and they have a connection with some of they have a connection with some headquarters throughout the country. I'm not sure exactly how many offices have a connection, but if you're interested in getting the SFR product, you probably should talk to sport and see if your office actually has those two products in your system. And only the participating offices have access at the moment. And I don't know, but maybe I can and give you the contact information, the sport contact information for you to follow up on that.
Thank you. And one more question, unless something comes in the meantime, that I have for you is, how do you think the ongoing and future SFR development will improve mSFR?
Yeah, so one thing, I think I mentioned that already a few times, we're extending the product to colder region, and that will help us to do a better job in the mountains, and then the really cold areas where radar doesn't have a good coverage, then so that will make the mSFR product a much better, more useful product for people. Over ocean, we're adding that. then again, it's just basically we can contribute more to the mSFR product where radar doesn't do a good job, and also improve the product itself, the quality of it. So that will also benefit the mSFR product.
Okay, thank you. And we did get another question in here from Steve Rajowski. And can NBM snow ratio be used with the product?
I'm sorry, could you repeat that?
So the national blend of models snow ratio, could that be applied here to, to the product?
Okay, so is that the snow to liquid ratio?
Right.
Okay, yeah, if you have a product like that, and I wasn't aware of that, yeah, use that with the mSFR product. That will help you. You can convert the liquid to solid. I understand the solid is what the weather forecasters need. Yeah.
Okay, thank you. Thank you for fielding all the questions here. And I'm gonna turn it back over to Jordan.
Thanks, Nick. Thanks for leading that discussion, and thanks, Huang, for that excellent presentation as we head into winter. Some good work with microwave data and combining that with radar, which I think can be very beneficial to reduce the number of clicks that forecasters need to take to get information they need. So with that, you can see the contact information for the Tower S team up. If you have questions about the latest Tower S RPM, we've got great support for you. With that, hope everybody is doing well, and I hope you'll join us next week. Thanks, everybody, and take care.
Thank you.